In our previous video, I showed you if you were given a formula, how to get the percents of each of the elements in that formula. Not too hard, you follow a formula, how to get the mass of the element over the whole mass times 100, and you've got a percent composition. What we're going to do in this video seems like it's just the reverse thing. What we're going to do is we're going to be giving you the percent composition of the elements, and from that you're going to determine the formula. First thing we can determine is an empirical formula, and then I want to teach you how to go the next step to a molecular formula. It's the reverse process, but it's much more complicated, okay? So if at any point, what I want you to really do, I'm going to give you the steps to follow. I want you to take the time to think, why do these steps give me the results that I'm looking for, okay? And if you can't come up with the why these steps work, it's hard to remember it. If you understand the whys, it's really easy to keep straight what's going on here. Okay, so steps. The first thing that you're going to do is assume that if you have a 100-gram sample and they give you the percents, that those percents can be treated as if they were grams, okay? So if it's 5% hydrogen, that's 5 grams of hydrogen. 20% oxygen, that's 20 grams of oxygen, because you're assuming the whole is 100, and each one of those percents would be how much out of that 100 that you have. Okay, that's the first thing. Now, what is a formula? A formula is a ratio of the numbers. We've got to get out of the mass world into the number world. So how do we do that? To go from the mass world to the number world, we're going to go to moles. Moles is a number, right? We can go from grams to moles of each one of those elements, and we know how to do that step. The third thing that we're going to need to do is divide by the smallest one. Why? Because a formula is the lowest whole number ratio of those guys. So we want to come up with the lowest possible numbers to put as subscripts. So we'll divide each one by the smallest one to give us those subscripts. Now sometimes when we do that, we don't end up with whole numbers. Sometimes when we do that, we end up with fractions. So if you end up with C1H1.5, okay? You wouldn't want to leave the subscript like that. And so what you'll have to do is multiply through. Let me just write what I just said. If you ended up something like C1H1.5 and we wouldn't put that 1 there, we couldn't leave it that way. So what it says is sometimes you're going to need to multiply through in order to give us whole numbers. And you got to think, what's the smallest number I need to multiply through by to get rid of that fraction? Well, if I doubled everything, that would be C2H3, and that would work, okay? So that's what I mean by step 4. Now in your textbook, they're really good about giving examples, and as of the recording of this, the textbook that we have has example 3.16, and 3.17 that show you, okay, here's examples where there's fractions, this is what you do about it. So you'll need to take a little time to look at those examples after we work through it where we're not going to end up with fractions, okay? So here's our example. Here's our first example. I have a compound, don't know what it is, but I know that 40.1% of it's carbon, 6.6% of it's hydrogen, and 53.3% of it is oxygen. Now we're going to follow those steps that I just described to you in order to come up with the empirical formula. What did it say? Step 1, to treat those percents as if they were grams. So I've got 40.1 grams of carbon, okay? I have 6.6 grams of hydrogen, and I have 53.3 grams of oxygen. So I did step 1. Step 2 says to convert those grams to moles. So for the carbon, I don't want grams of carbon, okay? I want moles of carbon. I go to the periodic table and I know there's 12.01 grams in a mole. So when I divide those, I will have moles of carbon, and it's 3.34 moles of carbon. Okay? The second one is the hydrogen. Okay, so let's do this in a different color just so I don't run into those others. It's kind of jam-packed there. That shows up differently, doesn't it? I don't want grams of hydrogen. I want moles of hydrogen. I go to the periodic table and it says that it's 1.008 grams in a mole, and that will give me the value of 6.6 3.53 moles of hydrogen. Okay? And now for the oxygen, I don't want grams of oxygen. I want moles of oxygen, and there are 16 grams in a mole, and that's going to give me 3.33 moles of oxygen. So now I've done step 2. Step 1 was this, step 2 converting to moles. What does step 3 say? Step 3 says divide each one of these by the smallest of the values. So I'm going to take the carbon and the hydrogen and the oxygen number and divide by whichever one of these is the smallest. Well, the smallest of the bunch is 3.33. So I'm going to take this value divided by 3.33, okay? And that is essentially very, very close to 1 for that one, okay? So I have 1 carbon. I take 6.53 and divide by 3.33. Now when I divide that, I don't get exactly 2. It's 1.96, okay? And we're not going to do 1.96. 1.96 is very, very close to 2, so there would be 2 hydrogens, okay? And then 3.33 divided by 3.33 would be 1 oxygen. So now I know the empirical formula for this compound. The lowest whole number ratio is CH2O. Now this is just an empirical formula. You need to know this is not the molecular formula. This is the lowest whole number ratio because that's all the system can tell me. By dividing by the smallest, I get the lowest possible whole numbers. Now remember, just to reiterate, if one of these is a fraction, let's pretend. Ready for pretend? Pretend's going to be in pink right here. Let's pretend when we divided these we got 1.5. Oh, or maybe we got, when we divided this, we got 1.49, okay? That's pretty much 1.5. So that would be 1.5, but we wouldn't want to leave it at 1 point. I mean, we can't keep 1.5 to 1. We would then want to multiply through to get rid of that fraction. So we double everything, and it would be C2H3O2 if we were working off of that number, okay? So those examples, 316 and 317, we'll talk you through that a little more slowly. But you're dividing by the smallest to get an empirical formula. So there's our empirical formula. Okay, but we can't leave it there because sometimes what we need is not the empirical formula, but the molecular formula. So how do we go from an empirical formula to a molecular formula? Well, you cannot do it unless you know the mass of the compound, all right? If you know the empirical formula and approximate molar mass of the full compound, then you can obtain the molecular formula. That's the only way you can do that, okay? So how would we do that? This is what we know. The empirical formula is this. The molecular formula is some integral multiple of that. It's either 1 times this, in which case the molecular formula would be CH2O. If it's 2 times this, it'd be C2H4O2. If it's 3 times this, it'd be C3H6O2. One of these is the correct molecular formula, but I can't know that unless I'm given the piece of information there, the molar mass of the compound. Okay, once I know the molar mass of the compound, I'll know which one of those would fit. Okay, so how do we figure out what the multiple is? Is it 1 time it, 2 times it, or 3 times it? Here is the formula. You take the mass of the compound that you have been given divided by the mass of the empirical formula. Okay, and that would give you that integer that you're going to multiply it by. Once you know that, and it turns out to be 1 or 2 or 3 or 5 or 6 or 10, you multiply these subscripts by that number to get the formula. Now, it's one thing to know this formula down here. It's another thing to understand why that works. So I'm going to try to give you a non-chemistry example to help you with that, okay? A non-chemistry example. Let's do it over here in this space. Let's say that I went to the grocery store. Okay, and I got me a paper bag okay? And I put into that paper bag some coconuts. And I folded it up and I didn't let you see inside that bag, but I told you that this bag weighed 4 pounds, okay? I told you the bag weighs 4 pounds. That is the mass of the whole thing. Look at that, oh there, that would be the bottom number, the top number, the mass of the whole thing. The bag weighs 4 pounds. And then I told you that each little coconut weighs 2 pounds. And then I asked you, tell me how many coconuts in that bag. I bet you, by the way, this is a coconut. You can't tell that, but that's coconut. If I told you each coconut weighed 2 pounds, I bet you could figure out how many coconuts were in a bag. You'd figure out the multiple of how much more the whole thing is versus the one, and you would do 4 divided by 2, and you would say you had 2 coconuts in there. What if I told you, and I have no idea how much a coconut weighs, what if I told you each coconut was a half a pound? Okay, each coconut was a half a pound. Then I say, okay, I want you to tell me how many coconuts are in that bag. You would know that if you took the mass of the whole bag divided by the mass of the little coconut, that there would have to be 8 coconuts in that bag. And that is what this formula is kind of analogous to. If you look at the numerator, it's the mass of the whole thing, the 4, okay? It's the mass of the full compound. In the bottom, in the denominator, is the mass of the empirical formula, the little guy, okay? The little guy, the coconut. All right, that's going to give you how many of these little guys it takes to make the whole thing. And we'll be able to work through an example, okay? So, look at these numbers. The carbon, the hydrogen, the oxygen, these are the same percentages, give or take a little bit, okay, as these. And if you go through and use those numbers instead of these numbers, these will just slightly change, but you'll end up with the same empirical formula. So let's just put a big star next to the formula. Those percentages will give you, with an experimental error, you're going to come down to these whole numbers. So we know that the empirical formula is this. In order to use that previous thing, we need to know the mass of the whole thing, and they tell you it's 180, and we need to know the mass of this little guy here, the empirical formula. Okay, so the first question is, what's the mass of the empirical formula? So that's the first thing we're going to answer. Well, we only have 1 carbon, that's 12.01, and we're working in AMU units because the formula, the whole formula mass is 180. So I'll use the AMUs here. So I have 1 carbon, I have 2 hydrogens, okay, and I have 1 oxygen. All of these in AMUs, and this will give me an empirical mass, which is what they're asking for right there, of 30.04. Okay, so that's the first number. The next question says, well, if you know that, what's in? To get in, okay, what we need to do is take the mass they're giving me of the whole bag of coconuts. That's the mass of the entire compound, divided by the mass of each individual coconut, okay? That's the mass of the little formula unit. And this is going to give you a value of 6. It will always be a whole number, or very close to it, given that you're dealing with measurements, you know, with an experimental error. You're going to find the nearest whole number. So now we're ready to get what's being asked to begin with. What is the molecular formula? Well, it's 6 times the little units, okay? So it's going to be C6H12O6. So now at this point, we know the molecular formula, knowing 2 pieces of information, the empirical formula, which we might have to do all the work that we see there, all of this work to come up with that. But once we know that, we'll take the mass of the whole thing that has to be given to us, or we have to be given information to get that piece of information, divided by the mass of 1 unit, and that will tell you how much more you have to multiply those subscripts through in order to get your correct answer. All right, so you can see that starting with percentages and turning them to grams and doing this work to get an empirical formula, taking that empirical formula and finally getting a molecular formula is a whole lot more work than if I gave you this and said, what's the percent of each thing? There's a quick and easy formula to get the percents. It's more involved, but it's the reverse, what we're asking, okay? Reverse of the previous lecture. You'll need to do a lot of practice of that, and we'll practice it some more in class with your group members.